I am Krishna. Welcome to Krishna's Classroom. We begin with another episode of Riemann's Stieltjes integral. We pick up the thread from where we left it last time. Recall, we gave an example of a Riemann Stieltjes integral with a specific choice of the function alpha. So we consider the interval 0 to 3 and then we considered a alpha. We define alpha as follows. X square for x belonging to 0, 1. Then this is equal to 1 for the interval x belonging to 1, 2 and x square minus 2 on the interval x belonging to 2, 3. Now this is a continuous on certain parts but has a jump discontinuity at x equal to 2 of magnitude 1 unit. Okay, as you can see. So the graph of the function is something like this. Then it goes like this, and then at 2, so this is 1, then 2, and then it just goes like this. This is y equal to x squared, and it goes up to say something like at 3 it is 9 minus 2, so it is 7. It is 7. This is the point. Now, if you look at this, this defines a new length for intervals on the interval 0 to 3. So we are interested on, so you have a function f. So the problem is whether this is R alpha on 3. This is a term where alpha is as defined in this way. Now we made certain observation. Okay. So if you choose a bounded function, any bounded function on the interval zero to 1, okay, if you choose a function f belonging to R on, okay, let us define f as f. And let us choose f continuous on 0 to 2 plus epsilon. 0 to 1 plus epsilon. I do this way. And then choose union 2 minus epsilon to 3 on this part. So this is the choice that we make, and f any bounded function on one plus epsilon to 2 minus this way. Like this, where epsilon is some given positive number. Epsilon is some positive number. Small enough so that 1 plus epsilon 2 minus epsilon is contained in 1 this one. That's the choice. You can even choose f to be on this part a Dirichlet function, which is not Riemann integral. Okay. In fact, you can replace this f continuous by f Riemann integral. That's this. So you can write f Riemann integral belongs to R on. Okay, so with that choice, you see that you can show that f belongs to R. Okay. What I want to impress upon you is that no matter how you define it on the interval 1 to 2 or 1 plus epsilon to 2 minus epsilon, 1 plus epsilon to 2 plus epsilon, we make it even quite worse, on the worst type of oscillation that you can bring in, like the Dirichlet function. Still, the function would become Riemann integrable. This is because of the following facts. You take any AB, you take any xi minus 1 to xi contained in the interval 1, 2 has its alpha length that is because, see, you can write this, I use this notation. And you put alpha here to designate it, define this. So this is called the alpha length. This is called the alpha length interval A. Now what you can show is this. If xi minus 1 xi is contained in 2. For other places you can easily calculate it. And one more thing that you observe is that the alpha length of 2 minus delta to 2 plus delta. This is equal to, I have computed this last time, or limit of this delta tending to 0 of interval this alpha length of this. I meant 1 here, not 0. So this is equal to 1. So you see that here there is a weight coming, 1. And this is important. And that contributes an extra term in the integral. So you get a term in the integral which will be simply, so the integral is going to be turn out to be 0 to 3. This is equal to integral 0 to 1 f d alpha plus the integral 1 to 2 will be 0. So you get eventually here a contribution coming from here. This is equal to f 2 plus integral 0 to 2 to 3. This is the integral. Here you are free to take f in any way, except that it should be bounded. That's all. Okay? It need not be Riemann on that. Now this happens on every interval where the alpha length of subintervals are 0. Okay? So this is the important part. So in short, what have we achieved from the usual Riemann integration? We have now generalized the length of intervals using the function, the monotonically increasing function alpha. Okay? So a new concept of length has been introduced. So it is in a way a generalization of the usual Riemann integration where you choose alpha x equal to, if you choose alpha x equal to x, and R alpha reduces to the class R. Okay, this is a special case. But this is more versatile in the sense that from the discontinuities you get some extra terms into the interval, into the integral. Now this is one of the important things, and as I have described in the case of the rod, the moment of inertia of the rod, if you assume that there are certain points on which if you have some weights, then it makes some extra contribution to the moment calculated, moment of inertia calculated. So exactly the same situation. However, I want to tell you, still we have not got out of the obsession with the intervals. But we are still subdividing the interval 0 to 3 into subintervals, or we are introducing a partition in the traditional way. All that we have done is, now we have chosen to talk about the length of intervals using this monotonically increasing function alpha. The alpha length of the interval a b has been introduced. This is a generalization, and you have already seen that with the alpha being chosen as a step function, you can get the infinite series or finite series also into the mold of an integral. Now this is one advantage. So there is a unification of series and the integral. So that is one of the achievements of this. So I think with these remarks, let me now pass on to a usual result that we come across, which talks about the change of this. Which we normally do for computing the integrals. Okay, let's look at this part. So we have a very nice theorem which justifies the change, and under what circumstances it does justify. So we look at the theorem. Suppose phi is strictly increasing continuous function that maps an interval AB to AB onto AB. From the conditions we have assumed on phi that it is strictly increasing, you see that this is also a one-to-one. Okay. Therefore, the inverse exists. Now, suppose alpha is monotonically increasing on AB and F belongs to R. On A. Define beta and G on AB by beta y equal to alpha of phi y for y belonging to AB, then gy f of phi y then alpha belongs to G belongs to R beta and integral a to b G d beta equal to integral a to b f. So you can go over to a new interval and work out the integral. You get that, you end up with the same. Okay, so you will have to define from f through the map that you have from the interval ab to small ab phi, you will have to define both beta and g, and we shall examine this, how this comes, then it will be very clear what is happening. Okay, so let us look at the proof of this here. So we work out the proof of this here. Now before we embark on the statements of the proof, we will do the following. We will examine what is the statement of the theorem. Okay. And then that will give you a good insight into what it is. So what you have is, you have an interval capital A to capital B of R, and then you also have an interval AB of R. So what is given is a map from AB to small ab. Phi is a strictly monotonically increasing function on AB. Okay, that is the property of phi. So you see that this phi is one-to-one on A. So you will write here. So phi is continuous. Phi is one-to-one. Phi is one-to-one. Therefore, phi inverse exists as a continuous function from small ab to capital A. Okay. Now we look at the following functions. So what you have is, you have x. This has x naught. This has x1. So there is a, sorry, this has xn, and there is a partition here. So which is xi minus 1 to xi. You have usual partition. So you have a partition P of AB. So A equal to the partition x0, x0, x1, x2, etc., xn, A. So that's the partition. Now what happens? Each xi gets mapped to the inverse map. So there is a corresponding partition for the interval AB. So let me write that as something like, say, tilde. P theta is a partition of A capital B. Now what do you have here? You have phi of yi equal to xi, or phi inverse of xi equal to yi, for I equal to 0, 1. This is what you have. So that's what you have from the about the map phi. Now let us define, look at the maps beta and G. See, alpha is defined from, alpha is defined from here to R. So you have now something defined from here, beta. What is beta? Beta is equal to, beta is then equal to alpha composition phi. Beta is equal to alpha composition phi. So you take any y here, it gets mapped to some x here, and then alpha maps that. So the composition of, so beta is equal to alpha composition phi. Now what more is given? You are given an f belonging to R alpha. Given f belonging to R alpha. So it is defined from here. So you have an f defined from here. Now you see that there is a corresponding map G defined from AB to R. How do you get that? Okay. So you get that as F composition phi. That means you start with some element here, map it here, and then apply F. So you get here this is your G equal to F composition. These are the maps. Okay? So you have a G from G defined as F composition phi. Now the question that you ask is, suppose f is given to be Riemann integrable with respect to alpha here. What you want to conclude or what do you expect from all these maps is that G is R beta for the interval AB. Let us see whether this is true or not. Let's compute the upper sum and the lower sum and so on. So you have one side, this is the upper sum and lower sum. So you have, say, Mi into beta but what is this? Mi is where Mi is, so this is the upper sum. So let us write down the upper sum. This is identified. U P tilde G beta. This is what you are writing. Now this is equal to sigma mi beta yi minus beta yi minus 1. This is it. Where mi is equal to supremum of gx on the interval yi minus 1. Similarly, you have L this is equal to sigma small mi beta yi minus beta yi minus 1. Again, I will only from 1 to 2. This is what you have, where small mi equal to infimum of gx over y. This is what you get. Okay. Now one can see that the following. So what is G? G on the interval yi minus 1 to yi you are taking is determined by f on the interval xi minus 1 to xi, and they have the same value. Therefore, you see that what you get is this is the same as mi on the interval xi minus 1 to xi of f. Similarly, small mi for g on the interval yi minus 1 to yi is the same as small mi on the interval of f corresponding to f. I mean, both are the same. So what you have is the following. So we observe the following. Let me write down. Observe that mi, which is equal to supremum of over yi minus 1 yi gx is equal to supremum of over xi minus 1 to xi on the interval this of f of x. Similarly, small mi infimum of yi minus 1 to yi of gy, which is equal to infimum of on the interval xi minus 1 to xi of fx. Now these are two facts that are very crucial to our computation, and therefore one would immediately get that u p tilde g beta is equal to sigma mi beta yi minus beta yi minus 1, which is the same as sigma mi alpha xi minus alpha xi minus 1, which is equal to u p f alpha. Similarly, u l p tilde g beta is in the same way equal to L P F alpha. These two are. So these are the two crucial equalities that you use here. Okay? And therefore, what do you get? See, you are given. So F is Riemann integrable. Implies there exists a partition P. This is true for any partition. A partition P of AB such that, let me take this out. Such that I'll put here given epsilon positive, in order to chosen epsilon, there exists a partition P of the interval AB such that UPF alpha minus UL less than X. So hence we have P tilde, a partition of AB, capital AB, determined by phi. Therefore, you have now U, see, U P tilde G beta minus L P tilde G beta. This is equal to U P F alpha minus L P F alpha, which is less than X. Therefore, for the given epsilon positive, there exists a partition P tilde such that U P tilde G beta minus L P tilde G beta, which implies G belongs to R. On A. So that's the result that you get. So we have proved that G belongs to RB. Now, of course, by simply taking the supremum and infimum, etc., you get the upper integral, lower integral, etc. You can prove that. So now it is clear that you need a few lines. You have the UPF. So you get say the upper integral, the lower integral, and so on. From this, now one can deduce that integral a to b g d beta, this is equal to integral a to b f. So that completes the result. So that completes the proof of the theorem. Okay. This corresponds to what is called a change of variables that we usually work out. Now we look at a special case. Special case. Take alpha x equal to x and beta equal to 5. Assume phi derivative belongs to then integral a to b fx dx, this is equal to you get this, get the corresponding g. So what is it? Integral a to b f of phi y into phi derivative y. This is simply the substitution. Okay. This is essentially the kind of because if you substitute x equal to phi y, because you recall our map, the map phi is from the interval ab to the interval small a. Okay, so you write x as phi y, then dx becomes phi derivative y dy, and this will become simply f of phi y, and the limits of integration will be from capital A to capital B. So that's the change of variables that we have, which we know. That's a very simple observation that we make. Okay, now we have already done this, but just for something like completeness, we recall the fundamental theorem of calculus for the ordinary usual Riemann integration. Just for completeness of something, please write down this. So fundamental theorems fundamental theorem of calculus. This is for ordinary Riemann integral, which we have elaborately considered in the last series of lectures, but still we recall it just for the sake of completeness. Okay. This is connecting, in fact, looking for what's called the antiderivatives. Okay, so we'll just quote the theorem, and this has been done very elaborately. Okay. So, theorem that f belongs to Riemann integral on AB set fx equal to integral a to x ft dt, x belonging to the interval a. This implies f is continuous on AB further if f is continuous at C belonging to AB then capital F is differentiable at C, and we have f derivative of C equal to f. Now this we have considered very elaborately in the lectures on Riemann series. So I am not going into any explanation on that. So what is to be observed or what is to be noted here is that the f derivative, see, we get f is continuous on AB. That's that you get once small f is Riemann integral. But only at the points of continuity of f, small f, you get capital F differentiable and f derivative equal to f. That's just the remark that I want to make. Then we have the next result, which is the fundamental theorem of calculus. This is called calculus. Now this is, in fact, if f belongs to Riemann integral on AB and if there is a differentiable function capital F on AB such that f derivative equal to small f, then integral a to b fx dx is given by capital F minus capital F of. Now this is fairly clear. We are assuming that f is Riemann integral, and at every point f derivative is equal to f, then we take this. This is the integration of parts. All these results we have discussed in detail earlier. Suppose capital F and G are differentiable functions. On AB and F derivative equal to small f and G derivative equal to small g, both Riemann integrable, both in R, then this is the integration by parts. Integral a to b capital F x gx dx equal to fb minus fa ga minus integral a to b fx gx. So this was actually working with the capital F into G and then working on the derivative of it. So that's fairly simple to work with. That we have discussed in detail. So work on the function. Now I think I'll stop here today and then take up the vector valued function and their integration in my next lecture. So thank you very much.